Hello everyone, my name is Liz McCormick from Bryn Mawr College. Here's an example problem in physics involving two-dimensional motion and relative velocities. You wish to row straight across a 63-meter wide river. You can row at a steady 1.3 meter per second pace, and the river is flowing at 0.57 meters per second. And the question is, what direction should you head in order to go straight across? And how long will it take you to cross the river? So this is a problem involving relative velocity. And since we know the speed and direction of the water flow, and we know the speed with which you can row, we have a little bit of information of how these relative velocities combine. So first, let's make a sketch of the relative velocity vectors to get clarity around the physical situation. So we know that you'd like to go straight across this river. Let's denote that with a vector going straight up in this situation. And let's call that vector V, and I'll use a bar to denote that it's a vector. And I'll use the subscript, that's the velocity of the rower with respect to the shore. So I'll call that rower with respect to the shore. We also know that the water is flowing, and let's assume if we're going straight across this way up, that the water is flowing to the right. And notice that its magnitude, 0.57, is a fraction of the magnitude of your rowing velocity of 1.3. So I'll try to get that length approximately correct. So that vector might look something like this. And this would be the velocity of the water with respect to the shore. Try to make that a W and an S. And then as we're thinking about how these vectors are related to one another, your velocity going across the water as the rower plus the velocity of the water is going to result in the velocity of you with respect to the shore. So the vector here that we also know would go here, and this is the vector representing the velocity of you as the rower with respect to the water. And now we can clearly see how these vectors are related to one another. We see that, I'm going to grab here the pointer, we see that this resultant vector V of the rower with respect to the shore is just the sum of the velocity of the rower with respect to the water and the velocity of the water with respect to the shore. And that makes sense. Tail to head gives us this resultant vector. So the vector equation we're working with then, we can write down over here to the right, this is vector equation, the velocity of the rower with respect to the shore is just the vector sum of the velocity of the rower with respect to the water and the velocity of the water with respect to the shore. And it's kind of a nice kind of mnemonic to recognize that you can think about these W's canceling to give you the rower with respect to the shore. Now, in order to vectors to be equal to one another, you can think of this as a vector on the right-hand side equal to the vector on the left-hand side. These vectors, in order for them to be equal to one another, their individual components have to be equal to one another. So now that we've sketched this out schematically, in order to answer the questions, we're going to solve this equation algebraically using the vector components. In order to get the vector components, we're going to need to define a coordinate system. And in this situation, a Cartesian coordinate system seems a pretty good choice. We'll take the x direction to be along the horizontal and the y direction to be along the vertical. So our vector, the velocity of the rower with respect to the shore is definitely going in just the y direction, so we can write that vector as v sub rs is going to be the magnitude v sub rs, and v sub rs is going the y direction, so we'll write that in terms of j hat, the unit vector in the y direction. Our velocity for the water with respect to the shore, the current, is also flowing in only, has a component in the x direction, which we can denote in terms of the unit vector I hat in the x direction, and it has a magnitude v subscript ws for water with respect to shore. The next vector we want to write in terms of x and y components is the vector of the rower with respect to the water. And of course, because this vector is going to have both x and y components, we're going to write that vector in terms of an angle. And let me specify that the angle we want to use is this angle right here between these vectors. We'll call that theta. Now we're going to be, in order to take the projections of this length on the x and the y directions, we want to remember with a right hand in a right triangle, where this is our 90 degrees here, the sine of the angle theta is going to be the opposite over the hypotenuse, and the cosine of the angle theta is equal to the adjacent over their hypotenuse. All right, so let's write our vector equation for the velocity of the rower with respect to the water. And that's going to be the velocity of the rower with respect to the water. It's going to have an I hat component and a j hat component. And the I hat component is going to be the magnitude of the speed of the rower in the water. And we want the projection of this vector, on the x direction, or this direction here, right? So we know that we're going to have then, to get this, we're going to have the opposite over the hypotenuse. So that's going to be the sine of theta. So we're going to write that as the sine of theta then. And you might notice that this component of this vector is actually in the minus x direction, minus I hat. Similarly, for the component of this vector that's projected along the y-axis, we're going to be using this adjacent over hypotenuse, so that'll be the cosine of theta. And we will write the magnitude of the rower, speed with respect to the water, times the cosine of theta. There we go. So now we have equations, or I should say we have expressions for our three vectors in this problem. We're next going to move to another slide, and what we'll be doing is setting up the vector component equations, where in order for these vectors sums to be equal, the components of each of the vector sums must be equal, and we'll do that next. Let's make some room here so we can continue to work on this problem. Next, I want to write down the x component equation. We'll do that up here. What we want to do is collect all the terms that are in the I hat direction and do this sum right here by for the I hat vectors first. And so you'll see velocity of the water with respect to the shore is going to be this VWS, and we're going to pick up this component too for the velocity R of the rower with respect to the water. So that will give us then, and then let's go back just to be clear. What's the x component of this vector? Well, this is the rower with respect to the water. Is going to go in this position, so that's this guy. But the vector of the rower with respect to shore, right here, the rower with respect to shore has no x direction, so that'll be a 0. There we go. So we're going to have a 0 equal to the vector, the rower with respect to the water, which is going to be our minus v RW sine theta. And then the final term is the vector of the water with respect to the shore, and that's just the magnitude VWS. Similarly, we'll write the equation for the y component. And again, the y component of V sub rs points in the y direction. It's right here, so we'll just have V sub rs. And now we want the y component of V sub rw. And V sub rw, the y component is right here. So we have V rw cosine theta. And then finally we're going to be looking for the y component of VWS. And VWS, of course, is this guy here, and there's no component in the y direction. It's all in the x direction. So that just gives us a 0. So this tells us our two equations and we'll note that we've got two equations and two unknowns. Theta is unknown, and our velocity of the rower with respect to the shore is unknown. We do know the velocity of the rower with respect to the water. That's this ability to row at 1.3 meters per second. And we do know the velocity of the water with respect to shore. That's this flow rate of 0.57 meters per second. So first, let's solve for the angle theta using our x component equation. So we'll write this down here. So if I go ahead, I can write theta is going to be equal to the inverse sine of this ratio of the velocity of the water with respect to the shore over the velocity of the rower with respect to the water. That's going to be equal to the inverse sine of our ratio of these two velocities. So the water speed is 0.57 meters per second, and the speed of the rower is 1.3 meters per second. And if you put that into your calculator, I think you'll find our theta comes out to be 26 degrees. Now this kind of makes sense, knowing the relative lengths of these two vectors, which we tried to draw in proportion here. Having this angle theta be about 26 degrees makes sense. Now, knowing that theta is 26, we can then plug that into this equation, knowing that the velocity of the rower with respect to the water is 1.3 meters seconds, and we can get the velocity of the rower with respect to the shore. So let's do that next. Plug that in. We have the velocity of the rower with respect to the shore is going to be the velocity of the rower with respect to the water, which is 1.3 meters per second, and we'll multiply that times the cosine of 26 degrees. And this works out to be 1.2 meters per second. So the original problem asks us to figure out what direction you should head as you tackle the water. And of course we've discovered that you should head out 26 degrees upriver, so that between your paddling and the flow of the water you'll end up going straight across. The second question was, how long will it take you to cross the river? Well, now that we know what your speed is, which is what we just calculated here, and we know the distance across the river, we should be able to calculate the time it takes you to get across. So the time, let's try that again. The time, of course, is going to be equal to the distance divided by this velocity v rs. And so that's going to be equal to 63 meters divided by 1.2 meters per second. And if you work that out on your calculator, you get 52.5 seconds. So that's interesting. Just under a minute is how long it takes you to paddle across 63 meters with a cross current of 0.57 meters per second and your own ability to row at 1.3 meters per second. So in looking at this problem, there are several fundamental math skills you use to solve it. In the beginning, we had to have a good sense of graphically understanding the addition of vectors and how to represent them graphically. We then algebraically wrote down expressions for the vector components. So being able to take a vector, define a coordinate system, and find its components along those coordinate axes was a skill you used. And you also used a little bit of right-angle trig to understand how to find the components of vectors along those axes directions. And then finally, I would say there was a little bit of working with systems equations. We had two equations and two unknowns, and you had to use those two equations to determine those two unknowns, one after another. So if you wanted to brush up on any of those math skills that get used in these problems that are about relative motion, I would suggest you look at the right-angle trig module, the system of equations module, and the vector addition module. So have a look at those modules, get some good practice in, especially on those areas you feel a little rusty, and then come on back and try the do-it-yourself problem.